This proton on ethanol has a pKa value of approximately 16, while this proton on acetic acid has a pKa value of approximately 5. Remember, the lower the value for your pKa, the more acidic the proton. So with a lower pKa value, acetic acid is more acidic than ethanol. We can explain why by looking at the conjugate bases. If ethanol donates this proton, the electrons in this bond, the electrons in magenta, are left behind on the oxygen. So let's draw in the conjugate base. This oxygen would have 3 lone pairs of electrons, and one of those lone pairs would be the electrons in magenta. That gives this oxygen a -1 formal charge. Let's draw the conjugate base for acetic acid. If acetic acid donates this proton, then the electrons in magenta are left behind on the oxygen. So the conjugate base would have a carbon double bonded to an oxygen here with 2 lone pairs of electrons. And then on the right, we would have another oxygen, this one with 3 lone pairs. One of those lone pairs would be the electrons in magenta. So that gives this oxygen a -1 formal charge. Let's compare our 2 conjugate bases. Both of them have a negative charge on an oxygen, so there must be some other factor to stabilize a conjugate base. And that factor is resonance. So for the conjugate base on the right, we can take those electrons in magenta, we can take these electrons here, and we can move them in, and then we can kick off these electrons onto the top oxygen. So let's draw the resulting resonance structure. So we would have, for our top oxygen, we would now have 3 lone pairs of electrons around the top oxygen, giving that top oxygen a -1 formal charge. This oxygen would now have only 2 lone pairs of electrons around it, and the electrons in magenta moved into here. And these pi electrons, let me make them blue, moved off onto the top oxygen to give the top oxygen a -1 formal charge. So the negative charge on this oxygen is not localized to this one oxygen. It's spread out. It's delocalized. So there's actually some negative charge on this oxygen too. So remember, resonance structures are not perfect. In reality, it's really a hybrid of our 2 resonance structures. So the negative charge is spread out or delocalized over 2 oxygens. And when you spread out a negative charge, that has a stabilizing effect for the anion. So our conjugate base is stabilized by resonance. And since our conjugate base is stabilized by resonance, that means acetic acid is more likely to donate this proton. And that's why we see a lower pKa value. If we compare that to the conjugate base for ethanol, right, this is called the ethoxide anion, right, we can't draw a resonance structure. We can't delocalize that negative charge. That negative charge is stuck on this one oxygen here. And that means this conjugate base is not as stable. It's not stabilized by resonance. So that means ethanol is not as likely to donate its proton, and that's why we see a higher pKa value for ethanol. So when you're trying to figure out the more acidic proton, draw the conjugate base and look for resonance. Here we have an organic compound, and our goal is to determine which is the more acidic proton. Is this the more acidic proton, or is this the more acidic proton? So let's say a base comes along and takes this top proton here. Well, the electrons in this bond in magenta would be left behind on this carbon that I just circled in magenta. So let's draw that conjugate base. We would have our ring, we would have this carbon double bonded to this oxygen. This oxygen has 2 lone pairs of electrons on it, and the electrons in magenta would remain on this carbon right here in magenta, which gives that carbon a -1 formal charge. Don't forget that carbon in magenta also has another hydrogen bonded to it, but I'm not drawing it in on the conjugate base just to make things easier to see. Let's say a base comes along and takes this proton. So that would mean the electrons in dark blue would remain behind on this carbon in dark blue that I just circled. So let's draw that conjugate base. So let me draw in our ring here, and then this oxygen would have 2 lone pairs of electrons on it. The electrons in dark blue, The electrons in dark blue would end up on this carbon in dark blue, which gives that carbon in dark blue a -1 formal charge. Let me draw that in. Again, remember, this carbon also has a hydrogen bonded to it, but I'm not going to draw it in on the conjugate base because it makes it easier for us to see. Which of those two conjugate bases is the most stable? Well, the top conjugate base is stabilized by resonance. You could take these electrons in magenta and you could move them in to form a double bond. So let's go ahead and show that. The electrons in magenta move in here, and that would kick these electrons off onto the oxygen. So we would have now, when we draw our ring, we'd have a double bond here, and this oxygen would have 3 lone pairs of electrons around it, giving it a -1 formal charge. So the electrons in magenta moved into here, and the electrons in, let's make these light blue, the electrons in light blue moved off onto the oxygen to give the oxygen a -1 formal charge. Now remember, oxygen is more electronegative than carbon, so this oxygen here is better able to bear this negative charge than this carbon in magenta over here. So this, on the right, this resonance structure actually contributes more to the overall hybrid, but our conjugate base is stabilized by resonance. That's in contrast to this conjugate base down here. We have a negative charge on this carbon, but that negative charge is localized to that carbon in dark blue right here. We can't draw any resonance. We can't show any resonance stabilization, which means that this conjugate base is not as stable as what we drew up here, which did have some resonance stabilization. And that means that we found our answer. The more acidic proton is the one that has the conjugate base that's resonance stabilized. So this proton that's next door to this carbon double bonded to the oxygen, that's on a carbon that's next door to this carbon double bonded to the oxygen, that is the acidic proton. And this is something that will come up later in the course. It's very important to understand.